So welcome back. Today we are going to look at biological networks. I'm going to introduce you to a very interesting concept of biological networks. You may have heard of networks by different names like graphs and so on. So we look at a history of graph theory. What you see on your screen now is a beautiful rendering of a yeast protein interaction network. So let's look at the history of graph theory. It's got a very fascinating history, and how does it go? So basically this was set in the year 1735 in the Prussian city of Königsberg, and today it's in a particular part of Russia around the Pregel river. So the residents of the city had this question. So is it possible to set out from my house? You see the map of the city on your screen. So the city's residents had a question: is it possible to set out from my house? My house could be anywhere in the city, and the city is connected by beautiful bridges. As you can see, there are 7 different bridges. So can I start from anywhere in the city, cross these 7 bridges and get back to where I started, basically go back home, right? And this was a very interesting question that the city's residents had, and this question needed to be solved, and so the mayor of the city wrote to Euler, right? And I think no discussion of any math can be complete without paying our respects to Euler. So Euler's solution to this problem laid the foundations for graph theory. So this is in fact Euler's caricature. You see that the image is a little old, from it's from a 200-year-old journal. So what was Euler's contribution? So he took this sort of picture that you see here, and he made this into this kind of a caricature, simplified caricature, wherein we have a few different islands in the city which he denoted by capital letters, and a few bridges. You will find it, maybe you can strain your eyes and see those, a few bridges, 7 bridges in fact to be precise, denoted by small letters. So what did Euler do? He wrote this very nice letter back to the mayor. Thus you see, most noble sir, how this type of solution bears little relationship to mathematics. Right? So Euler actually started thinking that graph theory has little connection to mathematics, although today it's become an integral part of data science, machine learning, and every field that you can name, and of course biology, which is what we are going to focus on in this course. And he says, I don't understand why you expect a mathematician to produce it rather than anyone else, for the solution is based on reason alone. And but he said that it was interesting because he could not solve it just using algebra or just using geometry or just using the art of counting. Right? So he needed to expand the horizons of mathematics to solve this problem. So what did he do? He took this picture and converted. He actually didn't draw it in this form. We are very familiar with this kind of a picture today, where you draw these vertices or circles or nodes and connect them to others with edges and so on. But what Euler did was he showed that there is no Eulerian circuit, in his honor we name it that way, in this graph. So what did Euler show? He showed that if you start from, say, the blue node, you cannot visit all the different edges and come back to the original starting blue node in this graph. So he said that this is not possible. And today we say that there is, and this has very interesting applications, in fact, for genome sequencing, for read assembly of reads that you get from a next generation sequencer and so on. But today we will just focus on what Euler showed. So for example, if you started here, let's say you went here, and let's say you went here, you came back here, you came back here, and you came back here, you've missed out 2 bridges at least. You must have had this fun thing in school, that can you draw this kind of a picture without raising your pencil off the paper. This is exactly, this happens when an Eulerian path or an Eulerian circuit is possible. An Eulerian path essentially visits every single edge in the graph, whereas an Eulerian circuit returns to the same starting point. So if you don't return to the starting point and still completely traverse all the edges in the graph, it is an Eulerian path. It's a circuit if you come back to the starting node. But let's not worry about all of these. This is just to say how graph theory, which is a very interesting branch of mathematics and computer science, had very humble beginnings in the quest for city's citizens to find a path in their city, right, to basically traverse all the bridges in the city after a nice dinner meal or something. Okay, so what are graphs? Graphs are a very, very important theme in computer science, and a graph is typically defined as G, V, comma E, where you have a set of vertices V and a set of edges E, which consists of pairs of vertices from V. We basically say that E is a subset of V cross V. So if you have a Cartesian product of the set of vertices, so every pair of vertices is there in the set V cross V. So some subset of those are going to be present in your list of edges. Okay, and these graphs are often referred to as networks. For example, there could be road networks, social networks that all of us are very familiar with, or in the context of biology you have metabolic networks, gene regulatory networks, and you also have other interesting collaboration networks, co-authorship networks, movie actor networks, scientific citation networks, and so on. And these graphs are classified elaborately, which influences what kind of algorithms we can run on them and things like that. The first important classification you need to learn about is what is a directed graph versus an undirected graph. So what is a directed graph? A directed graph, there is a notion of direction in connection, meaning A is connected to B, but B may not be connected to A, meaning you may have a path from A to B, but you may not have a path from B to A. And you can imagine this in many networks. I will just tell you in a moment. But formally, when you say a graph is undirected, then if AB is an edge in the belongs to the list of set of edges in the graph, it implies that B comma A is also in the same set. Whereas in this graph on this here that you see, let's say this is A and this is B. You have a path from A to B, but there is no path from B back to A, no edge back from B to A. Right. So we call these directed edges or directed links and so on. These are called as nodes or vertices. Okay. So this is a directed edge from A to B, but there is no directed edge from B to A. Of course, there is a path from B to A. If you say this is C, you can go to A from B through C. You can go from B to C and then C to A. And now some examples. Road networks between cities are typically undirected, right. So if you think of highways, they are undirected. Well, the same NH4 will take you from Chennai to Bangalore, and the opposite, right. So you have a parallel opposite edge in some sense, will take you from Bangalore to Chennai. Right. So technically you can think of it as two directed edges, but you can represent them as an undirected edge. Whereas inside a city, you don't have that luxury because you have many one-way roads, and if you have a road from A to B, the same road may not be possible. You may have to go through quite a few other roads to get back to your starting point, because a particular road may be a one-way road. In the space of social networks, you can easily imagine that Facebook is typically undirected because A and B are friends. So A is B's friend means that automatically B is A's friend. Okay. Whereas when you look at Twitter, you may follow a celebrity, right, but that celebrity may not follow you back. So there is a notion of direction. So some people have lots of followers, means that they have lots of incoming edges, but they may not follow so many people, meaning they have not so many outgoing edges. Okay. And in the space of biology, you have protein networks which are undirected because there is just a notion of A and B are interaction partners and things like that, or they are functionally associated with each other. But in the space of gene regulatory networks, you have A activates B, B will activate some other C, C might repress A but have nothing to do with B, and so on. So you have a clear notion of directionality in these gene regulatory networks. And then you have this very important notion of weighted versus unweighted graphs. For any kind of graph, you may have weights that tell you what is the either cost of a particular edge. Typically, that's what that's how these weights are typically modeled in computer science, or they could also mean, say, strengths of interaction or probability in biology. They could mean strengths of interaction or probability in the context of biological networks. This is a bit of a departure from what you see in typical graphs, but you will see that graphs are basically a model. Okay, I am going to tell you later on, I will show you that graphs are essentially a model to capture a particular kind of interaction between certain entities, right. So, certain entities and their relationships are cast as a graph. So, how does this happen, or it is up to you. How do you want to cast a particular road network or a metabolic network or a social network into a graph, right. So, what would you choose for the nodes, what would you choose for the edges, and what would you choose for the edge weights? All of you have used Google Maps. So, anytime you perform a search on Google Maps, how do I get from place A to place B? It basically solves the shortest path problem on a graph, and by a shortest path, you might have seen that Google actually gives you 3 options typically. It could be like the shortest route, the cheapest route avoiding tolls, or it could be the fastest route. So, the best route based on distance, based on cost, or it could be based on time. So, you have different kinds of weights that are attached to your edges. So, what are the nodes and edges in a road network? The nodes would be junctions in the city where multiple roads essentially meet, and the edges will be the roads themselves, right. So, every road counts for an edge. So, now you want to find the shortest path from a particular place to another, and you can perform the search on a graph. So, here is a weighted graph. So, you have a node like say A and B. The cost of going from A to B is 5 kilometers or 5 minutes or 5 rupees, whatever it is, or in the context of protein interactions, A and B have a 5% chance of being connected to each other or something like that, right. So, there is only 5% evidence from different experiments that tell you that A and B are going to be connected, and so on. So, you have these kinds of inferences that one can typically build from these graphs. So, you have a notion of directed versus undirected graphs that we just saw, and then this notion of weighted versus unweighted graphs. And there are other graphs. For example, the graph that you see on the left is a sparse graph, and the graph you see on the right is a relatively more dense graph. So, what is a sparse graph? It has less number of edges compared to what is totally possible in the graph. So, you have a total of, suppose you have a graph with n nodes, you have n choose 2 edges that are possible, right. But only some of them exist in your first graph that you see on the left, but a lot more exist in the second graph, in the dense graph that you see on the right. And then there is this notion of a labeled graph versus an unlabeled graph, wherein you have nodes which have labels and so on. So, for example, these two graphs are not equivalent if, or isomorphic as one would call them, if you label them. If you did not label them, they are very similar, because you have one node that has 2 connections and 2 nodes that have 1 connection each. But here there is something that changes, right. So, you see that B has 2 connections, whereas here you see that C has 2 connections. So, they are no longer equivalent, these 2 graphs. Okay. So, these are just simple terminologies. Then you have the notion of bipartite graphs. A bipartite graph is defined as a graph which you can color using 2 colors, so that the adjacent nodes do not have the same color, right. So, that is exactly what you see here. You have nodes with 2 colors. You see nodes of this color are never connected to nodes of the same color. Again, you see nodes of this color are never connected to each other, right. So, you can, using 2 colors, you can color the graph such that adjacent nodes do not have the same color. This has an interesting application, and this occurs naturally in a lot of scenarios. For example, you can have metabolites connecting to reactions and reactions connecting to metabolites, and you can have authors connected to papers and papers connected to authors and authors never connecting to each other. So, let us think of an interesting network, the co-authorship network, right. So, you can think of a network where you have people who write research papers together and so on, and you can think of them being connected. But suppose I wrote them in this fashion. I have 3 authors, A, B and C. I am not really sure what is happening here. Did A, B write a paper together and B, C write a paper together and C and A write another paper together, or A, B and C wrote one paper together and A and C wrote another paper together, or whatever. So, there are multiple possibilities that you may infer from this. On the other hand, I could write this as A, C, B wrote a paper. So, you can think of this graph being projected, you can think of this graph being projected to this graph. So, what you see is this graph is actually bipartite. You have nodes of 2 different types, 2 different colors, 2 different shapes, any which way you think about it, and there are no connections between nodes of the same shape or same color. So, there are paper nodes that will not connect to each other, and there are circle nodes or people nodes that will not connect to each other. All people write a paper, and this is how this is emitting. So, very common membership kind of network. So, you could think of these as actors in movies. I have an example coming up for you, or you could think of these as people and places, where very important, because we use these for social contact tracing, which became very important during the COVID pandemic and so on. So, these kinds of networks have very interesting applications. So, this is a bipartite graph. You can also think of it equivalently as a hypergraph. What is a hypergraph? In the kind of graphs that we have looked at so far, every edge connects only 2 different nodes. We said E is a subset of V cross V. Every edge connects only 2 different nodes. Whereas, I was showing you that this does not give you enough information when you are looking at these kinds of networks, right. So, in a co-authorship network, I do not know if A and B wrote a paper together, or B and C wrote a paper together, or A, B and C wrote a paper together. For example, here if A and B had written another paper together, that would be linked like this. So, here if you project it, you will still get the same thing, maybe you could have a different edge weight or something, but you can also have another representation in terms of what is a hypergraph. So, think of this graph. So, here you have multiple people. So, you have A, B, C, D, E, F and G, let us say. Now, I know that B, C and D wrote a paper together, A and B wrote a paper together, C and D wrote a paper together, E, F and G wrote another paper. So, there is a different kind of, you can have more than 2 people involved in a hyper edge. Okay. And what is a hyper edge? So, the set of hyper edges in a graph. So, here the edges is no longer a subset of V cross V, but it is actually a power set of V. Any combination of vertices can fall into your edge list, hyper edge list. So, you have this very nice way of, and there is a way to transform a hypergraph into a bipartite graph and so on. So, these are very interesting ways to represent more complex systems without actually losing much information that you would normally lose when you just simply projected it onto this kind of a graph that you see, right. So, this graph has less information, whereas this graph has more information, in fact complete information that you have available. There are some other interesting terminologies like a clique or a complete graph. So, a clique is nothing but a part of a graph which is fully connected. This is a complete graph in fact, and so is this. And these are 2 cliques in a graph, right. So, clique is a subgraph, a small subset of the graph, nodes and all their edges, which is fully connected. Okay. And then you have this notion of a walk on a graph, wherein you go from A to B, B to C, C to A and so on in a given order and so on. So, you basically start with a node, traverse an edge and go to another node and so on.